The current location of testing the VIC driver circuit. Stanley A. Meyer. Okay, so this is the circuit I'm working from. I better save it, I just changed it. This is version 1.2, and as you can see I relabeled these VA, VB, and VC, and then 0 volts. So VA and VB are tied together currently, and VC is set at 5 volts peak to peak, as we can see there. So if I set this at 5 volts, I have to drop these two down at least to about 3. If I set this at 10 volts, then I can set these at 5 volts and it's fine. But I can't set this one at 5 volts peak to peak and these 5 volt peak to peak. It doesn't work. One has to be offset. This one basically has to be higher than this one, or this first transistor never switches on. So here's what I've got. I'm currently measuring across all of the collectors. So this, and this in order. 1, 2, 3, and 4. Alright, so 1, 2, 3, and 4. So I'm going to show you what I found. So right now the signal's off. We'll just turn it on. So let me come out a little bit so you can see what we got. So the yellow trace is the first stage, the blue is the second. You can see it's inverted. The pink or purple is the third stage, and the green is the tip 120. So I'm going to zoom in pretty close so we can see what's happening. This is actually like really close. So you can see there's a slight offset, but whenever the signal is turned on the first stage, the second's turned off, the third is turned on, and the fourth is turned off. So the tip 120 is actually on when it's off. Okay, so you can see our measurements there, our voltages, peak to peak on the right. Get a good look at that. So the thing to note here is that all of them are turning on almost identically at the same time. Now I do have this resistor and capacitor in there, and I'll show you what's going on there. Talk about probing a circuit. Anyway, okay, so now we're going to actually look at the backside. Okay, so this is actually when the circuit is turned off. When the pulse coming in is turned off, the coil is actually turned back on, but they're not at the same rate. You can see this big delay, so I'll switch back. Alright, so here's the front, they're all pretty well the same. Here's the back, they're pretty all well a mess. So now what I want to show you is what it looks like with the, actually I can just do it now. Now don't forget the signal coming in is supposed to be inverted, and that's why, because it is actually inverted. So I'm going to disconnect that 0.33 and 22K resistor. So I'm disconnecting them, and you can see that yellow trace. I'll hook it back up. You see that little peak right there? That's the collector of the first transistor, channel yellow. So that little peak you see is actually measuring right there. You can also measure it here on the base, of course, through there, but I'm currently just measuring it there. So I'll disconnect it. Okay, it goes away, and I'll reconnect it. If I can get it, there we go. Okay, so now I'm going to actually move the last probe, currently measuring the collector of the tip 120, and I'm going to move it and measure this point right here, and something really interesting happens. This is where it goes back to the PLL. So let me show you. Okay, I didn't do it yet, but remember that trace. I'm actually going to go out a little bit so we can kind of see. Again, this is where the signal, the output is turning on. Okay, so I'm going to move that trace right now. Okay, so as you can see, what it's measuring is how long it takes to get the coil to come back on to full saturation. So that point going to PLL pin 3 is the saturation point, how long it takes for that coil to basically charge up to its full potential. Now, if I remove the feedback, if I remove this junction from here to here, if I remove that, okay, watch what happens. It's completely gone. It looks just like the exact same thing as on the collector. So I'll move it back. Okay, there's the collector, and there's across that actually, well, yeah, this point. So I'm gonna hook this wire back on. Okay, so like I said, I just disconnected it. So watch what happens when I hook it back on. Now we get that nice curve. Now, let's see. I'm gonna go ahead and raise the voltage. The voltage going to the coil is actually set at 5 volts. Yeah, about 5 volts. So I can turn this scale down, and I'm gonna bring it up to 12 volts. Okay. See what happens. It just goes up. The reason I got it down is because it pulls more current. You can hear it ringing now. But I'm going to bring it back down because it doesn't need to be that high. So bring it back down to 5 volts. Could even bring it all the way down to... Okay, there's 2 volts. So you can see the curve didn't change too much. So again, we're measuring the decay and the rise. So with that disconnected, you can see it's just a square wave, but when those components are all tied together like that, you get that nice signal there. So there it is across the collector, and there it is across that point going to pin 3. Now, I did add that 100 UF capacitor right here, and this power supply is, well, it's old, as you can probably see. It's very, very old supply. And all it really did was kind of smooth out, just a tiny bit of smooth out the signals on the first stage, on this very first one. So, measuring it here, it just sort of smoothed this out, which is, you know, again, these two are tied together, so that makes sense. I don't know if that's just because of the noise on this power supply or what. I'm sorry. I was all wrong. This was set at 12 volts the whole time I was measuring current. Whoops. Gotta check those switches. Anyway, nonetheless, it's set at 12 volts right now. So this is a 12 volt signal, which if we go to measure, we can see it is right there. It's a little higher because of that little peak at the end. So I'm actually going to turn this, whoops, everything's pretty well in the same spot, but I'm going to turn this up so we can see. You can see when the coil turns off, there's definitely a little spike there. Let's actually look really closely to that. Hold on, let me get it set up. Alright, so when the coil turns off, you can see kind of what these signals look like. And you can really mess those up by changing the voltage here too low or too high. So that's exactly what I'm going to do. If I go too low, you can see things get really out of whack. You can actually start creating a weird ripple effect if I go too low. And if I go too high, the coil just turns on fully. So you got to get it actually just right about 3 volts for it to work right. So I'm going to do that exact same thing. I'm going to lower this voltage and check out this crazy ringing effect that you get. So again, the blue is on the second transistor on the collector, and you can see that crazy ringing there. And that is, this is hooked up. So if I disconnect the feedback, look, that ringing goes away. If I connect the feedback up, I get that ringing. So I don't know where that ringing's coming from. Maybe just the LC circuit there. I don't know. But I don't know, maybe that's something worth noting. Maybe not. Alright, note to self. I was measuring from ground across the collector the entire time. So technically the green trace was backwards the whole beginning of this video. And now it's correct. So forgive me, I'm not going to record it, but just take note. So now I'm measuring the ground potential. I'm basically measuring across here with my ground connected to this point and my trace connected there. So now if I turn this down and the trace goes low, the green one, it's pulling no current, so it's correct. And then going up too high, it stays on, which is pulling a lot of current. So anyway, just note to self, that whole beginning was screwy. But anyway, so let's look at the this thing when it turns off. Okay, so when it turns off, this is the mess that we get. So let me measure across that across this point here where the PLL gets tied to. Alright, so the yellow trace currently is measuring that pin 3 of the PLL here. So I find it really interesting that if you don't connect this feedback loop, or the wire going back to the base of Q7, if I pull that off, it kills the effect. If I hook it up, I get that back. And of course, let's change the frequency. Right now I'm at 5 kilohertz. So you can see how that would be useful if you're trying to find out how long it takes for the system to collapse. In this case, it was all backwards. It's not the amount of time it takes to charge. It's actually the amount of time it takes to collapse. But it also has that slope on the time it takes to charge too, I guess. Anyway, it could be some weird feedback. Maybe, maybe not. I still find it very, very strange, though, that when you bring this voltage down too low, you get this crazy oscillation. So, let's see if I can get this. Oh yeah, well, it's not going to hold steady. Hold on, change the trigger. Alright, so I still find it very strange, though, that the way that this whole thing oscillates. So if I bring it up, that goes away. If I bring it down, it's fine. And actually, now that I'm looking at it, look at the green trace, which is the across the coil. It's actually showing a very slight. When it's off, it's actually below. Anyway. Alright, last thing. So it is important to note, though, that when you drop this voltage across VA and VB too low to where things start getting really screwy, and you start getting this oscillation, it is very important to know that this 22K and this 0.33 nanofarad capacitor, this feedback, alright, when this all gets set just at the right levels, which is adjusting these, adjusts all that, right? When you get it just right, you do get these crazy oscillations at the beginning of the primary. But if I disconnect that feedback loop, okay, those go away. So plugged in, unplugged, plugged in, unplugged. So I don't know what that means for you. But for instance, if I set this to to the 5-volt peak to peak, and I set this to the 5-volt peak to peak, I mean, the coil's just on. It just kills it. But of course, if I bring this up to, there's 8, at least 8, then it comes back on. And of course, if I bring this down, I can get those crazy, I'm bringing this voltage A and B down, and I can get those crazy oscillations. So maybe that's supposed to happen, maybe it's not. Okay, that's it. Been messing with this thing for a while. I don't know if that's helpful, but I thought I'd document it in video format. So, there's the current schematic. There's the current circuit. The VIC is connected. Honestly, I don't know if these are connected correctly. It's just connected the way it was 3 years ago or 2 years ago, so I left it. It does have an iron core, and it does have an air capacitor at the value that's really close to an air capacitor of the cell. So, signal generator, voltage supply, and yeah. Today's date is, I don't know. It's Saturday, December 17th, 2016. In the lab, it's supposed to be 36 degrees today. And, well, quite frankly, it's cold out here. See ya.